later today, I hope. So exercise sheet 1 had 16 questions. Exercise sheet 2 had 8 questions. Can anyone spot the pattern? Is the decrease linear or is it exponential? I'm afraid it's exponential, so there'll be 4 questions, not 0 questions. So we'll be finishing those off on the last session. So today I want to finish this stuff I was talking about last time about applications of geometric invariant theory to G-complete reducibility and applications of this theorem. Got the number now. 4.1 I think it was, which said that H is G completely reducible if known if the orbit of a generating tuple is closed. So there's one more application of that I want to finish off. Now section 5, we're going to continue this theme, but to get more results about G complete reducibility we need some stronger tools from geometric invariant theory. So section 5 is going to be about optimal destabilizing parabolic subgroups, whatever they are. And the idea is that we want to generalize the, if you remember back when we were talking about the Borel text construction, that was this parabolic subgroup P of U, which had nice properties, where U is some unipotent subgroup of G. We're going to show that the same kind of idea works in general. I wanted actually to present the proof of this to you, or at least sketch the proof. About 1:30 in the morning last night, I was no longer completely convinced that this was a good thing. I think I managed to beat the proof into shape. It's quite long and complicated. So the structure of section 5 will be the first 2/3 of it will be going through this proof, and then the last third of it will be more applications to G-complete reducibility. So I won't be doing all of section 5 today. I'll probably get most of the way through the proof. If you get lost during the proof, then maybe don't worry too much, because at least the statement of the theorem I think is easy to understand, and then you'll still be able to follow the applications to G-complete reducibility at the end. So let's pick up where we were last time, which is this result here. Perhaps I'll write it on board so that we can see it when I go over to the next slide. So G com M is a reductive pair. So remember, this means M is a connected reductive subgroup of G, and the Lie algebra of M sitting inside the Lie algebra of G has an M-stable complement. And then we took the subgroup H of M, and then if H is G complete reducibility, completely reducible and separable, then H is M completely reducible. Okay? So this was the situation that we've looked at a lot, where we have a smaller reductive group M inside a bigger reductive group G, and we have a subgroup of H, and we want to know what's the relationship between H being G completely reducible and H being M completely reducible. So I sketched the proof of that last time. I'll skip through the next couple of pages there. Talk about proof. So here we have a corollary. Take a simple group of exceptional type and suppose the characteristic is good, and now take a subgroup of G that acts semi-simply on the Lie algebra of G, and then the claim is that the subgroup is GCR. So this is actually a special case of this proposition here. So we just need to see how we can fit this result, the statement, this proposition. So here we think of this as being M, and this as being G. So the notation is a little bit unfortunate, because this thing that we're thinking of as M, we're calling G, and before G was the big group. This is kind of unavoidable. At least we weren't able to think of a way of avoiding this notational problem. Now, we want to apply this theorem, so we need to know two things. We need to know that H is GLG. G is Lie algebra, remember, completely reducible. So remember, G acts on the Lie algebra by the adjoint action, and so therefore H also acts on the algebra of G. It's sitting inside G. This is because this is just another way of saying that H acts semi-simply on the Lie algebra, and H is separable. So why is that? Separable in GLG. That's because there's an exercise on the second sheet saying that any subgroup of a general linear group is separable. So that's fine. The other thing we need to know is that GLG comma G is a reductive pair. So we need to know that we have the Lie algebra. This is where it starts to get a little bit complicated. We have one group sitting inside another group. So the Lie algebra of the small group is then sitting inside the Lie algebra of the big group, which we can think of I've written this down in a slightly different way concretely before. If we think of this as GLN for some n, and we think of this as the n by n matrices, we can also think of this as the endomorphisms of the vector space. So that's the way we translate between these two ways of looking at the world. So we want to know that this Lie algebra has a G stable complement in here. Well, this thing has a non-degenerate bilinear form, conjugation invariant form on it. Okay. The entire algebra of n by n matrices has this symmetric, non-degenerate bilinear form on, and this is conjugation invariant, basically because trace is conjugation invariant. So here I just mean the usual product of matrices. So this guy always has this nice bilinear form on it. Why do we care about bilinear forms? Well, in the context of the special orthogonal group acting on some space, if you have a subspace that's stable under the action of the orthogonal group, then its orthogonal complement automatically gives you a complementary stable subspace. That's the significance of talking about bilinear forms in this context. And under the hypotheses in of the corollary, G also has a bilinear, non-degenerate, and symmetric, although that's not so important, form, killing form. Some of you may have come across before if you've worked with Lie algebras. And these two pieces of information together tell you that that this is a reductive pair. The argument's not so hard, but perhaps I'll skip it. But hopefully it's not too surprising that if we have lots of degenerate bilinear forms lying around, this is bilinear and I didn't say invariant. G action. So maybe it's not too surprising if we have lots of these forms lying around that this should be a reductive pair. And then we apply the proposition, which I foolishly just rubbed off, and the result now follows. And you get an analogous result for simple groups of classical type. You need a slightly different bound on the prime. You have to avoid the prime 2, but you also have to care about, if you're looking at SON, then you have to care about how P interacts with N. I think P should not divide N plus 2 or something. I forget the exact detail. So this is an interesting problem. Suppose we have a subgroup H of G, and H acts semi-simply on the Lie algebra. Does it follow that G is completely reducible? That's this open problem here. And the proposition just above the open problem says yes if H is a separable subgroup of G. And that's, I actually set that for you as an exercise in sheet 2. That's tricky, I think. There's quite a detailed hint. But it's an open problem whether this holds without the separability hypothesis. My collaborators and I spent quite a while trying to prove that, and we got a number of partial results, but we're not sure whether this is true in general. This leads to some interesting problems in representation theory. So if you're looking for a counterexample to this for a group of type AN, it turns out that kind of you know about the special linear group and the projective linear group, SLN and PGLN, which I told you about. But if n is divisible by p squared, where p is the characteristic of the field, you also have these so-called intermediate types, which are sitting in between SLN and PGLN. So you have this isogeny from SLNK to PGLNK, but in certain situations you can have groups sitting in the middle. And a counterexample to this in type AN must involve something like this that's sitting in the middle. You can't have a counterexample with SLN or PGLN. It's one of the things we proved. A lot of these problems involving G-complete reducibility, they're not sensitive to isogenies. So you remember that or at least I stated a result like that back in the second lecture, I think, that if you have an isogeny from a G1 to a G2, and you have a subgroup H upstairs, then it will be completely reducible upstairs, if and only if its image is completely reducible downstairs. What's tricky here is that isogenies don't always behave well at the level of Lie algebras. They're not an isomorphism of Lie algebras. So this map from here to here is not an isomorphism of Lie algebras if the characteristic divides N. So now let's move on to the next section, optimal destabilizing parabolic subgroups. And this is just summarizing the discussion that I made at the beginning. We had this nice, canonical was the word I used to describe it, parabolic subgroup P of U for a non-trivial unipotent subgroup U of G, which we could use to show that U was not G completely reducible. But it had the nice property that as well as this parabolic containing U, it also contained the normalizer of U. This is very useful. And what we want to do is to prove an analogous result not just for a unipotent subgroup U, but for any subgroup that's not G completely reducible. So the statement of the theorem says there's a parabolic subgroup P opt H of G, which shows you that H is not G completely reducible. So perhaps I should write that down. Not G completely reducible. We get this mysterious P opt H parabolic. So what does it mean that this parabolic witnesses the fact that H is not G completely reducible? That means that H is contained in the parabolic, but no Levy subgroup of this parabolic.
P opt is exactly this parabolic where no Levy subgroup contains H, you mean?
I'm sorry?
No Levy subgroup of P opt contains H.
That's right. No Levy subgroup of P opt. So that's what I recall. That's what I mean when I say that a parabolic subgroup is a witness to the fact that some subgroup H is not G complete reducible. This is what I mean. And this is the real point. The entire normalizer of H is also sitting inside. Okay. So the first application of this is going to be Clifford's theorem that a normal subgroup of a G completely reducible subgroup is G completely reducible. So if you get bored or lost in the rest of what I'm talking about, you might like to see whether you can prove that using the existence of this P opt. The proof, well, I'm going to go through the proof later, but the proof is quite short. It's just 3 or 4 lines once you have this optimal parabolic subgroup. And in fact, more generally, this is stabilized by any automorphism of G that stabilizes H. You can push this even a little bit further if you want to leave the world of algebraically closed fields. If you're working over some perfect field, K, and G and H are defined over K, then this optimal subgroup will also be defined over K. And the argument is you do the construction over K bar, and then you think of acting with the Galois group. The Galois group fixes H, therefore the Galois group also has to stabilize this optimal guy, and that tells us that the optimal guy is actually defined over this subfield H. I might mention this kind of stuff very briefly in the last lecture. What's going to happen is that I'm going to spend probably half of the last lecture finishing section 5, and then there'll be a little bit of stuff on some other topics for the rest of that lecture, maybe including non-algebraically closed fields. Okay, well, it's not clear from this description that P opt is unique. Maybe there are several parabolic subgroups that all have this nice property for this H. But what I really mean is that I've got a particular construction in mind. I'm actually going to construct this in a particular way, and this construction gives you a unique P opt H. So what's this opt subscript doing here? Opt is short for optimal. And we really are optimizing something. I'm going to define for you a real valued function on the space of co-characters, which is convex in an appropriate sense. So it will become clear what I mean by that later. And P opt will come from finding the unique co-character where this function attains its maximal value. Okay, there will be a unique place where the function attains its maximal value. This will give us a co-character, and the parabolic corresponding to that co-character, the P lambda, that will be this optimal destabilizing parabolic. So this arises from a more general construction in geometric invariant theory. We decided to call this the Hilbert-Mumford-Kempf-Hesselink-Rousseau theorem because it's a strengthening of the Hilbert-Mumford theorem. And Kempf, Hesselink, and Rousseau, all at about the same time independently, came up with this similar strengthening in the late 70s. Kempf's paper was 1978. I think Hesselink's paper was 1978 as well. I'm going to be following more or less Kempf's approach. So what does this more general theory say? So maybe it's helpful to draw a picture. So here's X, and here's the orbit G dot X, sitting inside the space capital X. So capital X is a G variety, and then let's assume the orbit is not closed. That tells us that somewhere sitting outside the orbit, but still in the closure of the orbit, there's a point X prime. And the Hilbert-Mumford theorem says that we can get to X prime by taking limit along co-character. Maybe there's lots of ways of doing this. Here's one. Maybe here's another one. We'll wander all the way over here. Let's take our time. We're not in any hurry, but we end up at the same place. Now, the idea of this optimality is that there's actually a co-character that takes us where we want to go more quickly than any of the others. Straight line. So the function that we're optimizing, we can think of as being, in some sense, the speed at which the co-character takes us from x to the limiting point. Okay? And I'm going to spend the rest of this lecture making sense of the statement, right? Actually writing down something rigorous that captures this idea. So that's what's written down here. We can construct an optimal destabilizing co-character that takes us outside the orbit as fast as possible and into the closed orbit. Remember, there's a unique closed orbit in the closure of this orbit, and it does that as quickly as possible. And we're going to show that this optimal co-character that we get, lambda opt x, is unique up to conjugacy in the unipotent radical of the corresponding parabolic. Okay, but if you think about this for a moment, this means that although strictly speaking lambda opt is not unique, because you have this freedom to conjugate it, you're not changing the parabolic subgroup associated to it when you change it, right? If you change lambda opt to u dot lambda opt, then lambda opt goes to u e lambda opt. I realise there's something that I forgot to tell you, and I better tell you what it is in a moment. But this is p lambda opt, because this u actually belongs to p lambda opt. Actually, it belongs to the unipotent radical. So the thing I forgot to tell you, and I'm kicking myself a little bit because I should have done it when I first defined y of g, and I need to tell you this, otherwise you're not going to be able to make sense of what I just said, is that g acts on y of g by conjugation. So if we have a co-character lambda and some little g and big G, what does the new co-character do to A, to some A and K star? It just, you evaluate the original co-character at A, and then you just conjugate by this fixed function. Okay, so probably even if I hadn't told you, you would have guessed what that means. This is really the only sensible definition that we have. So this is what I mean when I write u dot lambda opt over here. And I just realised now, standing up at the front, that I did say this later on in the notes, but I needed to explain this, otherwise you're not going to make sense of what that means. And just passing. So often we're interested in putting our co-character inside a particular maximal torus. What happens when you conjugate? Well, it's clear that you get a co-character on the conjugate of this torus. That's immediate from definition. Remember what this means. What does it mean for lambda to be in y of t? That means that the image of lambda is inside the maximal torus. Okay. So lambda opt is unique up to this conjugacy and a normalization condition, which I'll talk about more below. It turns out that we're going to want to define the notion of a length or the size of the co-character, and the reasons for this will become clear below. So we get this uniquely defined parabolic subgroup P opt, for the reasons that I discussed over here. And this construction is natural. Everything behaves nicely if you conjugate by some little g. So P opt of g dot x is going to be the conjugate of P opt of x by this same g. In particular, if you take a little g that fixes x, g dot x equals x, then that tells you that g has to normalize this over here. G dot x equals x, then p opt of g dot x is equal to g p opt x, g inverse. But this is it. If g dot x equals x, this is just equal to p opt of x. So this tells us that any little g that fixes x has to normalize this parabolic subgroup, and then as usual we're in a connected group, parabolic subgroups are self-normalizing, so that tells us that the little g actually has to live inside here. So this tells us that the stabilizer of the point is sitting inside the parabolic subgroup. So now here's how we prove theorem 5.1. We just we take a subgroup that's not G completely reducible. It's generated by some tuple of elements from G to the M. So it's topologically generated by some tuple of elements. Remember, we're always assuming that all of our subgroups are topologically finitely generated, even though that's not true. But there are just some little dodges you can use to get around that. If your subgroup is not GCR, then our fundamental theorem tells us that the orbit is not closed, and so this gives us this P opt. This gives us this P opt of H over here, and we define P opt big H to be P opt of this tuple H. And then the general theory says that the stabilizer of the point is contained in P opt of H. Well, what's the stabilizer of the point? It's the centralizer of H. Okay? Because remember, G is acting by the conjugation action on tuples, and saying that something fixes this tuple, that's saying that it commutes with all of the entries of the tuple, and therefore it commutes with the subgroup that they generate, which is capital H. Okay? We talked about that before. So the stabilizer of this tuple H is the centralizer of H.
So here this we prove that G belongs to normalizer of P, right?
Yes, that's right.
There is a typo.
Have I made a mistake? But the normalizer of P is just P.
Okay.
That's if you were paying very close attention, then maybe you would have spotted that in theorem 5.1 I talked about the normalizer of capital H, and here I've only proved something for the centralizer of capital H. So I'm cheating you. There's something. There's a subtlety here that I'm avoiding. So what's the problem? The problem is that we don't know that this parabolic we get, we don't know that it's independent of the choice of this generating tuple. Maybe if we choose a different generating tuple, we'll end up with a different parabolic subgroup over here. Okay? This is not a problem if we're talking about the centralizer, but this is a problem if we're talking about the normalizer. Okay? Because if we have some element that normalizes H, but doesn't centralize it, then conjugation is going to actually give us a different generating tuple. Right? And so we don't know that this is going to give us the same parabolic. So H is generated by some M tuple. We take little g in the normalizer, which is not in the centralizer. Let's call it, I don't really want to call this H prime because I've tended to reserve this notation for the limit I get when I apply a cocurrent. So let me put the tilde on top. Okay. My collaborators don't like it when I use tildes. Here. So if you conjugate this generating tuple by the G, we're going to get something different. Yeah? If little g doesn't centralize big H, then it has to not centralize one of the entries in the tuple, because the entries in the tuple generate big H. And then, how do we know that? How do we know that these are actually equal? Well, we don't. I don't know whether it is the case that these are equal in general. But there is a way of getting around this, which I'll just mention briefly, but not go into the details. You use Hesselink's notion of uniform S instability. So rather than looking at what a co-character does to a single point, we look at what it does to the entire set, capital H to the n. So rather than thinking of capital H having a single generating tuple, little boldface H, let's look at the entire set, capital H to the m, and think about what the co-character does to that. And this is more complicated, but this is more canonical, because you're not making some kind of choice of generating tuple. And if you do this, it turns out that the argument that I'm going to present to you, it all goes over in this slightly more general case, and you can end up getting an optimal destabilizing parabolic subgroup, this P opt, that is normalized, that is stabilized by the normalizer. Okay, so there's this little bit of subtlety here that I'm going to gloss over. So I think we've got about 15 minutes for our break. So let's get started on talking about this construction. So I'm not going to give you general proof, because there's lots of extraneous detail which will just bog us down and confuse everyone. I think probably the proof is long, and it's long and involved enough as it is. I don't want to make it any harder than is absolutely necessary. So let's look at a special case. So let's take V to be a G module. And this is nicer because it's easy to see what co-characters are doing in G modules, because you can talk about weights of maximal tori and see more explicitly how points are being taken to other points by co-characters. And let's look at unstable points. So this is terminology of Hilbert originally. So this means, what does it mean to be unstable? This means that the origin is in the closure of the orbit. This is an important notion if you're interested in quotients of projective varieties by reductive algebraic groups, which is also a big part of the subject. And the reason is that when you're forming the quotient of projective variety, this is an aside, you have some G modular V, you projectivize it, and G still acts on the corresponding projective space. Remember, this is the space of lines inside V. That's one way to think about it. And you have problems if you have some point little v which is non-zero, but the origin is in the closure of the orbit. Because you definitely don't want the origin in here. The origin is not going to give you a well-defined point of projected space, right? You form the projected space by taking the non-zero elements of V and factoring out by the difference relation. So this is a problematic condition when you're looking at quotients of projective varieties by actions of reductive groups. So this is where this notion originally came from. But for us, I'm just going to do this because it's nice and concrete. Okay. So rather than having an orbit G dot V that's not closed, and the closed orbit just being some random G dot V prime, the closed orbit is going to be just G dot 0, which is a single point. So by the Hilbert-Mumford theorem, HMT, Hilbert-Mumford theorem, you can find a co-character which takes this V to the closed orbit. Okay, Hilbert-Mumford theorem says that you can get from the point we started with to the closed orbit by taking the limit along the co-character. Closed orbit is actually just one point. So there's nowhere else. There's nowhere else for the co-character to go. Now let's analyse what's going on in terms of weights, the way we were doing a couple of lectures ago. So we pick maximal torus T, such that lambda is a co-character of this particular torus. We can always do that. And so we can talk about a set of weights of V with respect to T. So remember when we talk about weights, we have a particular maximal torus in mind. And this is going to be an issue here because we have to think about many different maximal tori. We have to keep track of what happens when we change from one to the other.
Excuse me, you
Yep.
take T so that lambda is in y of T.
Oh yeah, I've done. This is exactly the same thing I did the other day. I wrote my lambda upside down. I have no idea why I did that. Sometimes strange things happen between my brain and the board. So remember we have this notion of the support of V. So this is the set of weights such that when we write little v as a sum of pieces from the weight spaces, these are the weights corresponding to the non-zero pieces. This is a little v. So in general we write v as a sum over all of the weights, little v sub chi, where little v sub chi is in the weight space, big V sub chi, and then we throw away all the weights where this piece is zero, and the ones that we have left are the ones on the support. Yeah? And we saw when we studied these limits before, what does it mean for the limit to exist? It means that the pairing of lambda with chi is greater than or equal to 0 for all chi in support. So greater than or equal to 0 in order to get the limit to exist, greater than 0 in order for the limit to exist and be 0. Sorry, I should have said I want V to be non-zero. I want V to be non-zero. And I realised in writing this notes that probably it would have been better to write something like this to indicate the dependence of this on the maximal torus. Because after all, this is a set of weights, and when you're talking about weights, you have to specify which torus you're talking about. So we have to remember that later on when we were changing the maximal torus that we were thinking about. So let's write this very explicitly. Let's write the set, let's write the support of V. It will be some finite set of weights. Let's call them chi1 up to chi t. And so this is saying that we can write V as the sum of corresponding weight vectors. So really I mean V sub chi I. This notation is nicer. What happens when we hit this with lambda? Lambda of A dot V we know what happens to each of these. These are weight vectors, so we just multiply by some power of a. Whoops. And what are these exponents up here? It's the pairing of lambda with corresponding weight. And remember, we decided that because the limit is 0, all of these exponents are positive integers. Okay? So now let's ask ourselves, how quickly does this limit approach 0? So if I say just in the context of real analysis, no one's going to argue with this statement, of course, but the way we tend to think of these things is that if you make the, so here n is positive, if you make the exponent n larger, then you're going to 0 more quickly. Right? That's the kind of thing that we teach calculus students. So if you have some expression like this, how fast are you going to 0? Well, the speed is controlled by whichever of these exponents is the smallest. Yeah. So if you have an a squared v1 plus an a to the 7th v2, t equals 2 constants, then as a gets close to 0, then the effect of the a squared kind of dominates the effect of the a to the 7th. So we say the speed is determined by the smallest of these. So if we want to measure the speed at which little v is being taken to 0 by this co-character, we should do that by picking out whichever of these is the smallest. And that motivates this definition that I got down the bottom here. This stuff here is just what I said a moment ago, talking about the action of g on y of g. T from y of t, the integers, by mu v t lambda is just the smallest of these numbers. Psi lambda, box psi I. So psi I we can think of as being a function that takes co-characters to integers. Psi I of lambda equals lambda. So just a word about the notation. Before I was thinking of lambda as being some co-character that takes little v to 0. Now I'm thinking, maybe I should have been a bit more careful about my notation. Here I'm just thinking about lambda as being a completely arbitrary co-character. Okay? So if I put some lambda in, I'm going to get a positive integer or a negative integer or 0. Okay? And if I get a negative integer, that's saying that the limit when I apply this lambda to v is not going to exist. Okay? Because that's going to say that up here, one of these guys is going to be negative, and so the limit will not exist. So the limit will exist if and only if all of these guys are non-negative, and that will be the case if and only if the smallest is non-negative. Yeah? And the limit will be 0 if and only if none of these guys is 0, if and only if the smallest of them is positive. Yeah? So that's what I say on the next page, that the limit exists for a given lambda if and only if the value of this mu on lambda is non-negative, and the limit is 0 if and only if the value of mu on this lambda is 0. And then a little exercise that is going to appear on exercise sheet 3. What happens if you hit everything with g? Hit your point little v with g, hit your torus with g, hit lambda with g, and you just get the same thing as originally had. This is not a hard exercise, by the way. There's nothing complicated going on here. The stuff that's in the second half of this page is slightly more complicated. We can actually show that the value of mu on lambda doesn't depend on our choice of t. So maybe I'll explain this and then we'll stop for our 5-minute break. This is well, it's not so complicated, but it's maybe slightly tricky to get your figure out. So the claim is that the value of mu doesn't depend on the choice of maximal torus that your co-character is evaluating in. It's not depend on the choice of t. Because what we want to get in the end is we want to get a well-defined function on y of g. You give me a character, I want to give you an integer. Yeah? That's what I want. And at the moment I have this t dependence in. And so here's how the argument goes. So let S be the image of lambda. So S is a torus. Okay. So the maximal tori t, such that lambda is in yt, are precisely the t's that contain this S. Yeah? And the point is that the weight decomposition that we talked about before, we only discussed for maximal tori, but actually it makes sense for any torus. Any torus at all acting on a vector space, you get a weight decomposition. So you get V as a weight decomposition. For S. So we can write V as the direct sum of, let's call this phi sub S to indicate that we're talking about this S now, not about any maximal torus. Okay, you define weight and weight space in exactly the same way as you do for a maximal torus. And the proof that I sketch for why this works for a maximal torus, just works for any torus. Okay, so you can do this. Now let's think about putting this S inside a maximal torus T. Well, all of these weight spaces for S will be T stable. From the argument I gave in the exercise session, the argument where I said this works because T is connected, and then you pointed out, well, no, you don't need T to be connected. It just works because if you have two commuting operators, then one stabilizes all of the eigenspaces of the set. Yeah, so I've got the same argument. This is T stable. So each of these pieces, well, if it's T stable, we can regard it as a T module, and so it will split up into weight spaces for T. So this is going to be some over some finite set, say f of z2, some subset set of T would be common. So capital V we can think of as being the sum of weight spaces for big T, and each of these weight spaces for big S we get by grouping together bunches of weight spaces for T, right? But then for each chi in the set of weights for T that correspond to this space here, if we restrict this to S, these are all the same, right? So chi is the weight of T. If it's a homomorphism from T to K star. S is a subset of T, it makes sense to restrict this. Yeah. And then, and here's the crucial point, when you calculate this, this really only depends on the image of lambda. So it's the same for all these chi's. And in fact, you can just write this. Okay. Perhaps I'll leave the explanation there and leave you to think about this some more if you feel so inclined. Otherwise, I suggest you just accept this statement. Okay, let's stop for 5 minutes. At 12:38. So sorry about that. I had to pause a bit earlier. Okay. So this fact that the value of mu doesn't depend on the choice of t tells us that we can define mu sub v without the t subscript from set of all co-characters of G, z by mu v of lambda is mu v comma t of lambda for any t that lambda is living inside. Any t such that lambda. So where are we going? Let me just very briefly sketch the remaining steps in the proof so you can see where we're heading. So the first step is that we're going to make everything into real vector spaces. So at the moment we're talking about Z modules. Y of t is a free Z module. We're going to tensor with R. If I was tensoring with C, I could talk about complexifying. I don't think realifying is really a word, so I should use it. So we're going to be working with space like this, where we're thinking which is made up of real vector spaces stuck together rather than free Z modules stuck together. And then the second step is that we're going to define length, co-character, for reasons that will become clear shortly. And we're going to define f(v) of lambda is equal to mu v of lambda divided by the length of lambda. Okay, to make sense of this intuition about lambda taking points to 0 as fast as possible, we need to scale. We need to normalize somehow. That's one way of thinking of it. And then the third step is that we prove this local uniqueness. So here local means think of a fixed maximal torus. Show fb as local has unique maximum or I should could say attains a maximum at a unique point. Sloppy with my language. So I'm going to explain all these things more carefully in a moment. So locally inside each maximum torus, we get this unique lambda opt, where we're maximizing the value of this function, and then the final step will be global uniqueness, where we somehow stick all of these maximum tori together. This will give us our lambda. And so I'm hoping to get up to the end of step 3 today. Let's see how we get on. This is for me to write some useful formulas down that I don't want to rub out off. If I start rubbing off the stuff in here, then please shout at me. So we have equation 5.5. I was talking about. So you'll notice that I've dropped the t's here from 5.5. That's the maximum tori. That's because we don't need them. That's the point of what I was just saying. So this is 5.5. Now we want to prove another result. This just basically follows very quickly from some fairly standard and obvious manipulations. We're going to do something slightly more difficult. Have I skipped a page? Yes, I have skipped a page. Yeah, here we are. So lemma 5.6, there's a bit more substance in that. That's saying that this function mu v is invariant under conjugation by unipotent radical of lambda. Okay, well of course the unipotent, as you move lambda around, then its unipotent radical will change. But you take a fixed lambda and evaluate mu v there, and then do the same thing at u dot lambda, where u is in the unipotent radical, then you get the same thing. Proof uses this result lemma 3. So lemma 3.11. First step is to say uv u dot lambda. This equation up here allows us to shift the u from up here to down here. We get everything by u inverse. And so it's enough to show that this is equal to uv lambda. And the reason why we want to do this is that these guys here, lambda and u dot lambda, they're not living in the same maximal torus. And that makes life more difficult. Whereas here, lambda and lambda, they are living in the same maximal torus. So we can do everything in this fixed maximal torus. So we pick a maximal torus T, such that lambda is living in here. Let's call this guy n. So this is saying that n is equal to lambda paired with chi for some chi in the support. Yeah? How does this mu work? You look at the pairing of lambda with all of the weights in the support of B, and you pick the number that's the smallest. Yep, so there will be some chi tilde in the support of V, which is going to realise the smallest possible number. Okay? Now what happens when we hit this with U inverse? This will be the form V plus W, the sum W. Remember what lemma 3.11 says. That says that when you hit V with this U inverse, you're going to get some other stuff, and this other stuff will have maybe some other weights in its support that you didn't see before. But the pairing of lambda with those other weights will be greater than the pairing of lambda with the weights that we saw here. At least if V is a weight. If V is a weight vector, so in the special case that V is in the high tilde, then lambda with chi prime is greater than lambda with chi tilde, which is equal to n. Okay? So that's saying that in this special case, heading V with U inverse is actually not going to change the value of mu, because the value of mu you get by looking at the smallest of these pairings, and the stuff you've added is only involves weight bits which have greater pairing with lambda than this part that you're looking at. And the same argument holds more generally if V is not a weight vector, but as a sum of weight vectors, you look at the smallest of the weights that you see in the support, where by smallest I mean relative to the pairing. So this you maybe have to think about this argument a little bit to see what's going on. But anyway, this follows from this 3.11 proved a long time back, and this is the main reason why I wanted that level, actually. Now we come to I think it's the second step in the list, where I wave my hands and say, tensor everything with R. This makes sense for y of t. Y of t is a z module, so I can tensor it with R and I get a real vector space. That's fine. But now this is where I wave my hands. I say I can make y of g by gluing together these pieces y of t. Y of g is the union of the y of t's. Okay? The subtlety is that the given lambda can live in several different y of t's, right? Because there might be several different maximum tori that contain the image of my lambda. So there's some kind of identification that I'm doing when I'm sticking these y of t's together. And my claim is that I can do the same thing after tensoring with R. I can stick together these real vector spaces and get some space YR G. Okay? There's actually some stuff that you need to check if you go to do this, but I'm going to suppress the details. The other thing maybe to say here is that actually we can think of this as some kind of bookkeeping exercise. I am explaining things this way just because I think it makes the exposition go a bit more smoothly. You can actually you don't actually have to make this definition if you don't want to. Okay, it doesn't. So y of g, the genuine or honest co-characters you can think of as sitting inside this mysterious space that I've created, and the g acts on y of g, and I claim that likewise you get an action of g on this larger space. Now what I want to do is to extend the function mu v to a function not just on y of g. So remember the original the original mu v is going from y of g to z. I really want to be working with real vector spaces because there's a point where I'm going to use a compactness argument. I'm going to be looking at the unit sphere in some vector space, and I want to use compactness to say that some function attains its maximum. Yeah. Now I want to extend this. And I'm going to abuse notation and use exactly the same notation for the extended function as I did for the original function, so that I don't have to keep decorating things with subscripts and superscripts. Now, how do I do this? This is actually fine if I just work at the level of an individual maximal torus. Okay, so this is what we have for an individual maximal maximum torus. So remember the formula for this, mu v t lambda is the min over these weights and support of v psi I. Yeah. So this was the inner product of lambda with some chi I. This is a z linear function, right? Z linear. So after I tensor everything with R, I can extend this to an R linear function. Absolutely no problem. Extend psi I from R of t, which we call as y t, tensor with R, Z, ta. And there's a unique way to extend this in such a way that it becomes R linear. And then I just use exactly the same definition over here to define mu vt of lambda in this bigger space with these real linear functions that I've created. Okay, so this is actually there's not really any monkey business going on here. What's not so obvious is that then you can extend this to a function up here by gluing everything together. So you just have to believe me that this can be. And so, as before, first you do this at the level of a maximum torus, each maximum torus, and then you have somehow have some kind of checking to do if your lambda is living in two different maximum tori. And the problem is, what do you mean by lambda is living in two different maximum tori if lambda is not an honest co-character, but something living in here? That's what the problem is. You can make sense of these things. So anyway, you get this. This is what we're going to do. And then one more thing. So if we multiply 5.2, which you've all forgotten, so I'll write it down again. So 5.2 said lambda of A dot V is lambda of A dot V1 plus T. So these are these weight pieces. And this is A N1 V1 plus A NT VT, where AI is lambda I. What happens if we multiply lambda by a positive integer? Oh yeah, sorry, not maybe, definitely. Well, as I said before, so this is psi I of lambda. This is z linear. So if I multiply lambda by m, I'm going to multiply all of these by m. So if I'm talking about the co-character that takes v to 0 the fastest, if I have a co-character, I can make it take v to 0 faster and faster simply by multiplying it by higher and higher m's. Okay? So to make sense of this statement, I need to normalize lambda somehow. So what I really mean is, I want the lambda that takes v to 0 the fastest relative to the size of lambda. Okay? So I need some way of measuring the length. And that's what this notation here is doing. We have a so-called length function. So this is a function from y of g and its restriction to each real vector space is just the norm in the usual sense. In fact, it's the norm associated to an inner product. And when you have an inner product on a real vector space, then this allows you to define the norm according in the usual way. And in fact, I'm not going going to dwell on this, but this is important. The inner product is actually z value. So it comes from a z value inner product on the lattice y of t, which you can control sitting inside. So you can think of this here as being, in some sense, the z points of this real vector space. Okay. And we fix a length function. It can be shown that length functions exist. It can be shown that the unique up to scalar multiple if the group is if G is simple. If G is not simple, then you have some freedom to kind of multiply them independently on each simple factor. It is not clear that the optimal parabolic that we get is independent of the choice of length function. Okay, so this is something that I'm sweeping under the carpet, and this construction that I'm doing, the p opt that I get, might actually depend on the choice of length function. But we don't really care. We don't really care about that. And now here's this f that I was talking about before. It's this normalized mu you divide by the length. It's defined as non-zero elements of this space y sub r. And I really should have a v subscript here, but I decided to leave it to you. I'm not sure whether that's a good idea or not. So we get f from this mysterious space reals, and if we pick a particular maximal torus, then we can restrict this function to just this real vector space. And what we're going to do, and this is the local part of the calculation in terms I was describing before, is we're going to study this and show that this has there's a unique co-character sitting in here where this attains a maximum. And when I say character, I really do mean co-character. So there'll be some point in here where this attains a maximum, and then one can show that actually this point is an integer point in the sense that it belongs to here. Okay. A couple of facts about f. Just go through the calculation. Yeah, because I didn't tell you that the norm is G invariant. So look up here, we know that this is the same as mu v of lambda. This is from the lemma that we proved a moment ago. And downstairs, we get the length of lambda. This is because this length function is invariant under conjugation. Okay. So this step, this was previous lemma. This step, why the denominator is equal, that's because this G. Other property that we want. I think we're not going to need this today, we'll need it tomorrow. Lambda. I'll prove this as well. So here C is just some positive real number. Yeah. So this is mu v C lambda. Well, I told you that C is a norm, comes from an inner product, so we know what happens if we multiply a vector by a positive scalar. Its length just scales by the same positive scale, yes? So down the bottom, we get c times the length of lambda. What about up the top? Remember, mu v comes essentially from linear functions. It's the you take a bunch of linear functions, you apply them, and you take the smallest value that you get. And we know how linear functions behave when we multiply the argument by a scalar. We just put the scalar out. So we get here, so we get mu v at lambda over the length of lambda. Perhaps I should put t in here. It doesn't really matter. See a lot of unhappy people. I realise this is quite a lot to absorb. Okay, so I am going to get to the state and prove this local uniqueness result. Okay, and the good news is that the proof of this is something that I can explain very easily and draw a picture of that you'll be able to understand. So that's the payoff for all of this notation and stuff that I've been sitting on. I hope you'll be able to see what the idea of the proof is. You'll be able to see what's going on. So here's the statement fix. So fix a particular maximum torus and look at ft. Remember, that's the restriction of this f to this real vector space. And the theorem says there's a point where this function attains a maximum value, okay, first of all. But also it says that the place where it attains this maximum value is unique up to scale multiplication, regarded as a real point of this real vector space. But moreover, it says that this point is actually a z point. If we think of y of t as being like z points in this real vector space. So what's the picture here? So here's the origin. So think of the two-dimensional case. Think of this board as being r squared. Yep. And then sitting inside r squared, we have this lattice of integer points. So this full space here, let's think of this as being yr and t, and the black points are the points in y of t. And we have some function from r squared to r. And then the lemma says that this attains a maximum, and the set of points where it attains a maximum is a ray. Just wondering if the green pen is still lying around somewhere. Oh, yeah, thanks. This green ray, not including the origin, because our function f is not defined at the origin, because it involves dividing by the length of the vector and the length of the 0 vector is 0. So this is a ray r. So this is the set of points where ft attains its maximum. And the proof, although I'm not going to prove this particular part, tells you that this ray contains at least one of these black points. Yeah? And so what do I mean by this minimal condition? I'm saying there's unique lambda t. This set of black points, this is some discrete lattice inside this real vector space. So I look at this ray, there'll be a unique integer point on this ray that's closest to the identity. Okay? So that's what I mean when I say the length is minimal. Okay, this green ray I know it contains at least one black point, because the proof tells me this, and lambda t is the black point that's closest to the origin in the green ray. Okay? So now to prove this, here's my origin. Here's my, the whiteboard is yr of t. I have this function f, and remember that f is invariant under multiplication by positive scales. Okay? So I want to maximize this function. Because of this condition here, I may as well look on the unit sphere. I may as well look for the maximum point on the unit sphere. Okay? So let's take the unit sphere. Yes. Right? Because I know that if I take, say, the point here, if I move along this line here, I'm not changing the value of f. So I may as well look on the unit sphere. I'm going to take the special case, just because it makes the basic idea clearer, where, remember, this f involves a bunch of linear functions, psi1 up to psi t, and you take the minimum of those values. Let's just assume that we have only one linear function, just to keep life simple. So let's assume that ft of lambda is form psi lambda over the length of lambda, where psi is linear. So this is then a continuous function. Yeah, it's a continuous function. So on the unit sphere is compact. This is why I wanted a real vector space. So it attains its maximum. First year calculus, second year calculus. F gives a continuous function on the compact set S, and I'm just about out of time, but this won't take much longer. So S, so it attains a maximum. Value, let's call this value CT. So it depends on the choice of the torus. Say at lambda 1. Yes. Let me remove this line. So here's lambda 1. Okay? So f of lambda 1 CT. But lambda 1 is on the unit sphere, so remember the definition of f, you're dividing by the length of lambda, but that's just 1. So this is actually equal to psi of lambda 1. Now I want to prove that the set of points where f attains its maximum is precisely the ray through lambda 1. Okay? So suppose not, then I'll be able to find some other point somewhere on the unit circle where this also attains the same maximum. Okay. So suppose lambda 2 is an S, and f lambda 2 is equal to CT. I'm going to get, and let's also suppose that lambda 2 is not equal to lambda 1. I'm going to get a contradiction. Choose some C in the open interval between 0 and 1, so choose some C between 0 and 1, 3 be c lambda 1 plus 1 minus c lambda 2. So here's lambda 1 and lambda 2. I'll draw the line segment between the two, and lambda 3 will be living somewhere in here. Now what's psi of lambda 3? Psi of lambda 3, psi is linear. So psi of lambda 3 is c psi of lambda 1 plus 1 minus c psi of lambda 2. But psi of lambda 1 is ct, and psi of lambda 2 is ct. So I get ct. Now what can I say about f of lambda 3? F of lambda 3 is psi of lambda 3 divided by the length of lambda 3. But look at the picture. These two vectors have length 1. This guy obviously has length less than 1. So the length of lambda 3 is smaller than 1, and that means that f of lambda 3 is greater than ct. Contradiction. So what's the upshot of this? The upshot of this is that the set of points where f attains its maximum has to be precisely this green ray here, because if it wasn't, there'd have to be some other point on the unit circle where it attained its maximum, and then we get a contradiction. Okay, and then well, it's time to stop now. I'll just say it. You can show that, although this is not so clear, but you can show that there's one of these integer points lying on this ray. This is why we cared about the length function coming from the z valued bilinear form on the y-axis. And then once you know that there's one z point on here, then you can take the one that's the smallest to the closest to the origin, and this gives you your lambda t. That's it. So I'll stop there. Next time we'll do the global version where you look at maximizing this function on the whole of y.
Thank you very much. Now we have a break for lunch.
Maybe we'll ask to have lunch at 15 to 2.